Comparison of PID control algorithms, understanding how algorithm structure impacts control performance. Introduction. In real-world industrial control environments, not all PID controllers are created equal, despite having the same tuning terms. Proportional P, integral I, and derivative D controllers from different manufacturers may behave very differently. This variability arises from differences in how the PID algorithm is implemented, not just how it is tuned. Understanding these differences is essential for reliable controller tuning, system migration, and loop optimization, especially in complex or high-performance process applications. #Algorithm categories in use. Most commercial PID controllers fall into one of three structural categories: ideal, interacting, a clean implementation where all PID actions are based on the error, often used in modern digital platforms. Series, interacting with structural coupling, common in older analog controllers or when mimicking early pneumatic electronic systems. Parallel, non-interacting, each term PID, operates independently of the others, but tuning behavior becomes nonlinear with gain adjustments. Each category can drastically affect control loop response, especially when dealing with complex systems, cascade structures, or load set point sensitivity. Proportional action, gain versus proportional band. Some vendors define proportional action as gain, Kc, while others use proportional band, Pb, which is its reciprocal. Increasing gain makes a loop more responsive but potentially less stable. Decreasing proportional band achieves the same effect as increasing gain. Modern controllers may also allow gain to be applied only on error or only on process variable PV star. This distinction leads to dramatically different behaviors for set point tracking versus load rejection. Proportional on error, e.g. Honeywell Type A, produces sharp set point responses but can be sensitive. Proportional on PV, e.g. Honeywell Type C, smooths out set point transitions and may be preferred for supervisory or outer loops in cascades. Integral action, offset elimination with nuanced effects. Integral, reset action removes steady-state error but behaves similarly across algorithm types once tuning units are aligned. However, differences emerge in anti-reset wind-up handling, how controllers behave when output limits are reached. Although often subtle, these differences impact performance in systems with saturation-prone valves or long dead times. Derivative action, the most variable and misunderstood mode. Derivative is where the algorithms diverge most significantly, especially across manufacturers. Some controllers apply derivative only on the PV, others on the set point, which can cause large overshoots in tightly tuned systems. Some systems filter the derivative term to suppress high-frequency noise, others don't, leading to amplified measurement noise, jittery valve action, and even control instability. In series algorithms, derivative interacts structurally with integral action, modifying effective gains. This causes reduced usable derivative range, increased sensitivity to tuning ratios, D must often be less than I, complex phase interactions that shift control dynamics. Filtering derivative with a time constant tied to D is essential to prevent overreaction to noise or spurious PV spikes. Parallel controllers, ease of interpretation, risk of misuse. Parallel PID controllers offer mathematical simplicity. Each term is tuned independently. However, this independence can be misleading. Changes to controller gain indirectly affect the behavior of integral and derivative components. Lowering gain may reduce loop stability, contrary to intuitive expectations due to the scaling relationship between P, I, and D in the parallel form. This interaction is especially problematic in systems where aggressive tuning is required, e.g. fast loops integrating processes. Manufacturers like Bailey and Allen Bradley label parallel forms as non-interacting, while ideal forms are interacting. This terminology reflects how PID terms influence each other, but the control outcome can differ significantly depending on the chosen form. Real-world implications and best practices. Retuning is mandatory when switching controller brands or types, even if PID settings seem identical. Set point response behavior is algorithm dependent. Tuning for load rejection does not guarantee good set point tracking unless the algorithm explicitly supports it. Use filter derivative to preserve valve life, reduce actuator wear, and suppress false alarms. Choose algorithm forms based on loop purpose. Series for backward compatibility with pneumatic or legacy loops, ideal for modern DCS applications requiring predictable control logic. Parallel, when independent tuning of each term is needed, but with extra care in interpreting gain effects. PID algorithm selection is not just a software detail, it's a foundational design decision that impacts control performance, stability, and tuning philosophy. Controllers that appear similar on paper may diverge significantly in action due to internal algorithm structure, derivative filtering, and term interaction. To build effective, resilient control systems, especially in adaptive, cascade, or feed-forward configurations, engineers must match the algorithm to the process, understand vendor-specific behavior, and tune accordingly. Only then can the full potential of PID-based automation be realized. Critical differences between Honeywell and Yokogawa PID controller implementations, an analytical comparison of modern DCS-level control architectures. In modern industrial control systems, PID loops are foundational, but how they're implemented across platforms varies significantly. Two leading DCS vendors, Honeywell, Experian PKS, and Yokogawa, Sentenp, offer sophisticated PID functionality, but with differing philosophies in control architecture, algorithm structure, tuning interaction, and integration. A critical comparison of these systems based on core control principles reveals important implications for tuning accuracy, process stability, noise management, and engineering effort. Algorithm structure and tuning behavior. Honeywell's system offers two primary PID types. Type A applies proportional action on error SP minus PV, resulting in aggressive setpoint responses. Type C applies proportional and derivative action on the PV only, smoothing out setpoint transitions. This distinction allows precise structuring of cascade loops, with Type A better for fast inner loops and Type C more suitable for supervisory or outer loops. These modes share identical behavior in load disturbance rejection, but diverge sharply during setpoint changes. Yokogawa uses a combination of ideal, interacting, and parallel, non-interacting PID forms. While the ideal form offers predictable and intuitive tuning behavior, the parallel form gives users independent control over P, I, and D terms. However, this independence introduces nonlinear interactions. Changes in controller gain affect the effective strength of both integral and derivative actions. This makes the tuning response less intuitive, particularly in loops involving derivative action. In summary, Honeywell simplifies loop behavior through predefined PID modes, whereas Yokogawa offers more engineering flexibility at the cost of greater configuration responsibility. Derivative action and filtering. Derivative behavior is one of the most differentiated aspects between these platforms. Honeywell uses implicit derivative filtering, where increasing the D value automatically increases internal filtering. This approach limits high-frequency noise amplification and simplifies configuration, especially for users less familiar with frequency domain behavior. Yokogawa provides explicit filtering controls. Engineers can filter PV signals directly and adjust the filter time constant independently of the derivative tuning. Additionally, derivative on PV only is standard in Yokogawa's PID blocks, which prevents overshoot during setpoint changes. In noise-sensitive environments, e.g. flow loops, pressure control, or fast-responding temperature systems, Yokogawa's fine-tuned filtering and de-action isolation offer stronger noise suppression and valve protection. Honeywell's approach is more accessible and sufficient in general-purpose applications where derivative use is moderate. Integral action, reset behavior, and anti-wind-up. Honeywell's controllers come with integrated anti-reset wind-up, ARW logic, and external reset feedback, RF, built into the PID block. This ensures consistent behavior when control outputs hit actuator limits and allows smooth handovers during mode transitions. It's particularly useful in cascade and override architectures, where nested controllers need coordinated reset behavior. Yokogawa offers ARW as part of its PID block but requires explicit configuration. The advantage here is greater control. Engineers can customize reset behavior and even integrate reset bias logic into function blocks. However, this adds engineering overhead and increases commissioning time. Overall, Honeywell's ARW and reset coordination is tightly integrated and operator-friendly, while Yokogawa's implementation is flexible but hands-on. Cascade and feed-forward integration. Cascade structures in Honeywell's system are fully supported with mode tracking, set point passing, and automatic ERF coordination. Engineers can enable cascaded loops with minimal additional configuration, making it ideal for multi-loop systems in refining, chemical, and thermal plants. Feed-forward is built directly into Honeywell's PID block, scaled and biased internally. This allows for tight integration with load anticipatory control, improving disturbance rejection without needing external calculation blocks. In contrast, Yokogawa handles cascade and feed-forward logic through external function blocks. While this provides maximum architecture flexibility, it requires the engineer to design mode tracking logic, biasing, and override behavior manually. This is powerful in specialty plants with custom blending, adaptive logic, or constraint-based overrides, but requires deeper control design expertise. User interface, tuning tools, and operational transparency. Honeywell's control environment emphasizes operator clarity and deployment speed. Tuning tools are graphically driven with smooth faceplate transitions, status feedback, and real-time PID diagnostics. Engineers can access Experian loop diagnostics, RTune, auto-tuning, and loop simulation tools built into the platform. This is particularly advantageous for multi-skilled teams where engineers and operators share control responsibilities. Yokogawa targets engineering-centric users with tools like PRM, Xapilot, and Xasmoc. These tools support advanced control diagnostics, lambda tuning, model identification, and robust performance monitoring. They are ideal for plants investing in model-driven process optimization and adaptive control design. Honeywell shines in fast-paced operations requiring scalability and consistency, while Yokogawa is more powerful in projects that demand deep customization and fine-grained control modeling. Real-world implications. For high-throughput, continuous process industries like oil and gas, petrochemicals, and power generation, Honeywell's PID system offers consistent loop behavior, robust default protections, and simpler deployment of cascades, overrides, and feed-forward elements. Its architecture supports rapid loop rollout and ease of troubleshooting. In contrast, specialty chemical plants, batch operations, and R&D-driven facilities benefit from Yokogawa's capability to precisely configure PID loop behavior, filter structure, and signal logic. The level of configuration detail makes it ideal for multivariable coordination, complex reaction systems, and advanced process control layers. Each system is capable of high performance. The key difference lies in the division of labor between the control system and the engineer. Honeywell aims to streamline configuration and reduce design complexity. Yokogawa prioritizes full control transparency and system extensibility. Honeywell and Yokogawa reflect two distinct philosophies in PID control. Honeywell emphasizes pre-integrated logic, operator stability, and plug-and-play reliability. Its PID modes simplify tuning and cascade deployment while still allowing advanced users to fine-tune response and behavior. Yokogawa offers engineering flexibility, algorithmic control, and modular logic layering. It demands a deeper understanding of control principles, but rewards that effort with greater adaptability and precision, especially in complex or evolving processes. Understanding these differences is essential for control engineers, automation designers, and operations teams when selecting, tuning, and maintaining PID loops across diverse plant environments. Critical differences between Yokogawa and Invensys PID controller implementations. An analytical comparison of high-precision DCS control strategies. Both Yokogawa, Centum VPCS 3000, and Invensys, now Schneider Electric, Foxborough IA series, EcoStruxure Foxborough DCS, are long-established leaders in the DCS market, offering deeply engineered PID control frameworks. While both systems provide powerful regulatory control options, their philosophies of implementation, tuning transparency, and integration flexibility diverge significantly. Understanding their differences is crucial when selecting, migrating, or optimizing control strategies, particularly for plants with complex dynamic behavior, multivariable constraints, or advanced supervisory logic, algorithm structure, and loop behavior. Yokogawa supports both ideal, interacting, and parallel, non-interacting PID structures. This enables either intuitive, predictable tuning, ideal, or independent term adjustment, parallel, although parallel tuning can lead to unintended effects if gain interactions are misunderstood. Engineers must choose the form explicitly during function block configuration, giving them granular control over loop behavior. Invensys Foxborough, in contrast, traditionally uses a series algorithm, especially in legacy IA series systems. This format is historically rooted in pneumatic electronic control logic and introduces interactions between derivative and integral terms. These interactions change the effective behavior of P, I, and D terms depending on their relative values, making tuning less straightforward without conversion knowledge. Modern Invensys systems also support ideal algorithms in newer EcoStruxure and Foxborough Evo environments, but series forms are still widely used in existing infrastructure. Summary insight: Yokogawa offers dual form flexibility, predictable for most users, precise for advanced applications. Invensys maintains legacy continuity through series algorithms, with ideal forms available in newer builds. For controller migration or loop replication, algorithm form must be known. Settings cannot be transferred directly across platforms. Proportional and integral behavior. Yokogawa's ideal implementation provides consistent tuning interpretation across gain changes. In parallel form, engineers can tune P, I, and D independently, but changes in gain affect how I and D behave. Yokogawa also supports explicit integral limits and biasing, enabling fine-grained control in override or constraint-based loops. Invensys series PID form means that increasing D affects both I and effective P. For instance, when D equals I, the effective integral time doubles, and the usable derivative becomes constrained. This interaction can unintentionally shift phase response, particularly in fast loops. Furthermore, anti-reset wind-up ARW behavior differs. Yokogawa provides configurable reset limits, saturation logic, and external reset feedback. Invensys offers ARW as standard, but can be more controller-specific, e.g. in the FB107 PID block versus FCO blocks. Summary insight: Yokogawa offers modular and transparent integral control, adaptable for adaptive or ratio control loops. Invensys requires deeper understanding of series form interaction, manageable and stable loops, but less suitable for highly dynamic environments. Had derivative handling and noise management. Derivative action is where Yokogawa excels in configurability. Supports derivative on PV only as a default, enables explicit PV filtering with adjustable time constants, separates D-action filtering from signal filtering, offering layered protection against noise. Invensys, using series algorithms, applies derivative on error by default. This can cause overshoot and instability, particularly in setpoint-driven processes or fast-changing loops. While low-pass filters can be applied, they're often fixed or less user-configurable in legacy systems. In newer versions, filtering capabilities improve, but derivative filtering is still less transparent than in Yokogawa. In high-noise environments, e.g. flow control, steam pressure loops, this difference can significantly impact loop reliability and actuator wear. Yokogawa is stronger for noise-sensitive and derivative-heavy loops, offering precision filtering and D-logic configuration. Invensys can handle these loops with effort, but requires manual filtering, tuning, and caution with Series D interactions. Cascade, feed-forward, and constraint integration. Yokogawa's architecture uses function blocks to build cascades, feed-forward paths, and override logic. This modularity allows total freedom but increases engineering effort. The system supports external biasing, reset coordination, and multivariable signal conditioning, making it highly suitable for advanced blending, batch, or reaction systems. Invensys excels in integrated constraint control and override logic, particularly in the Foxborough Evo and IA series platforms. Their FCO, Foxborough Control Objects architecture, tightly integrates override, ramping, and saturation management into the PID loop. Advanced control templates allow cascade and ratio logic without needing extra blocks, enabling rapid deployment of complex control topologies. Summary insight. Invensys is more pre-integrated for override and constraint-heavy systems, e.g. power refining, whereas Yokogawa's function block layering is more customizable for adaptive or batch applications. User interface, diagnostics, and tuning tools. Yokogawa provides a function block-based interface with support from Exapolit, Exasmoc, and PRM, Plant Resource Manager. Engineers can analyze gain phase margins, lambda response, and simulation profiles. However, loop tuning remains an engineering activity, not a casual operator function. Invensys delivers graphically rich faceplates and diagnostic interfaces, especially in Foxborough Evo and Control Expert platforms. It emphasizes usability for both operators and engineers. Tools like LoopView, Insight, and Connoisseur APC Suite offer tuning, adaptive control, and performance benchmarking across loop portfolios. Summary insight: Yokogawa is ideal for engineer-led diagnostics, especially where model-based strategies are deployed. Invensys supports broader team roles, enabling both operators and engineers to manage loops effectively with built-in performance tools. Real-world implications. For greenfield projects demanding modular customization, adaptive control, and multi-loop synchronization, e.g. batch pharma, chemicals, food, Yokogawa offers a more flexible platform. For brownfield migrations, where minimizing loop disruption is critical, especially when migrating legacy pneumatic electronic control, Invensys with series algorithms can maintain loop continuity while gradually upgrading capability. In constraint-prone operations, e.g. refining utilities, Invensys offers tighter integration of overrides, ramping, and APC. In high-noise or high-frequency environments, Yokogawa's derivative control and PV filtering offer more tunable noise suppression. For plant-wide loop performance optimization, both offer excellent tuning tools, but Invensys tools are more operator-accessible, while Yokogawa tools are model-centric. Conclusion: Yokogawa and Invensys deliver powerful PID control capabilities, but with distinct design philosophies. Yokogawa prioritizes engineering precision, configurability, and model-based integration. It is well suited to dynamic, specialty, or multivariable environments requiring tailored control strategies. Invensys Foxborough focuses on structured integration, legacy continuity, and operational accessibility. It shines in large-scale industrial applications with complex override constraints and mixed-generation equipment. Each platform excels when matched to the right control environment. Engineers must evaluate not just loop tuning behavior, but also the control structure, diagnostic access, operator expectations, and plant-wide performance goals to select or integrate effectively across these two leading systems. Critical differences between Honeywell and Invensys PID controller implementations. A comparative study of structured automation logic in two DCS powerhouses. Introduction. Honeywell Experian PKS and Invensys, now Schneider Electric Foxborough DCS EcoStruxure Foxborough, are among the most widely adopted distributed control systems in process industries. Each offers a full suite of PID-based control capabilities, but their underlying control philosophies diverge significantly. This analysis examines how each system handles algorithm form, loop tuning behavior, cascade and constraint logic, and operator interaction, especially in the context of complex, multivariable, and high availability operations. Algorithm structure and loop dynamics. Honeywell supports Type A, proportional on error, and Type C, proportional on PV, PID structures. This dual-mode design allows users to tailor setpoint response behavior explicitly. Type A produces a more aggressive setpoint response, suitable for inner loops or fast control, while Type C provides smoother setpoint tracking, ideal for outer loops or supervisory layers. These options offer consistent load response with customizable setpoint behavior, and tuning remains intuitive. Invensys, rooted in series algorithm architecture, maintains legacy compatibility with earlier pneumatic and electronic systems. The series form causes interaction between derivative and integral actions. Derivative values influence effective integral time and vice versa. This interaction introduces nonlinear behavior, requiring tuning adjustments that aren't always intuitive, especially in fast loops or during derivative activation. While modern Foxborough systems do support ideal algorithms, many plants still operate with the series default for compatibility. Summary insight: Honeywell offers structured flexibility through clearly differentiated algorithm types. Invensys retains legacy tuning behavior, which may benefit migration scenarios but introduces complexity in loop dynamics unless precisely modeled. Proportional, integral, and reset behavior. Honeywell's PID logic is engineered for clarity and simplicity. Gain and proportional band are clearly linked. Integral action is consistent across modes. Anti-reset wind-up, ARW, and external reset feedback are seamlessly built into the PID blocks. Reset logic accommodates mode transitions, saturation events, and setpoint handovers without requiring auxiliary logic. Invensys, via its Foxborough Control Objects, FCO, and earlier FB107 blocks, implements ARW and reset logic with more manual setup, especially in older systems. In series forms, adjusting D affects the effective INP, making reset response more dynamic, but harder to tune unless algorithm-specific relationships are understood. In newer Foxborough systems, EcoStruxure Foxborough DCS, the function block language, FBD, supports improved reset management and integration with model predictive and override blocks. Summary insight. Honeywell prioritizes plug-and-play loop behavior with built-in coordination logic. Invensys maintains tuning consistency with legacy systems, but users must manage dynamic interactions between terms more deliberately. Derivative action and noise sensitivity. Honeywell uses implicit derivative filtering, where increasing D also increases the internal low-pass filter applied to the derivative term. This reduces measurement noise and simplifies operator use. Type C mode ensures that derivative action is applied only to PV, minimizing overshoot and instability on setpoint changes. Invensys applies derivative to error in its series algorithm by default. Without filtering, this can cause excessive reactivity and jitter in loops with noise or operator-initiated setpoint changes. While filtering is possible, it may require extra configuration and, in older systems, must be added via separate blocks. Later Invensys platforms introduced derivative on PV options and built-in filtering, but these enhancements are platform-specific and may not be uniformly implemented across legacy assets. Honeywell ensures safe and stable D action by design, while Invensys places more burden on the engineer to manage D-term behavior. This makes Honeywell better for derivative-heavy loops or fast response systems where actuator life and noise suppression are critical. Cascade, feed-forward, and constraint logic. Honeywell provides native cascade and override structures inside its PID and logic blocks. Mode tracking, setpoint propagation, and reset feedback are internally managed, making configuration clean, modular, and efficient. Feed-forward paths can be enabled directly within the PID block, with scaling and biasing handled through intuitive parameters. Invensys FCO framework integrates cascade and override behaviors at a deeper level. While feed-forward may need to be engineered through function blocks, Foxborough's override strategies are industry-leading, especially in high-integrity systems like steam networks, turbomachinery, and hydrocarbon refining. Foxborough excels in providing highly reliable constraint handling, especially when used with multivariable controllers and override selectors. Summary insight. Honeywell simplifies feed-forward and cascade deployment through embedded functionality. Invensys offers deeper constraint and override integration, particularly valuable in systems with high safety or performance-critical interactions. User interface, diagnostics, and tuning tools. Honeywell's Experian platform offers user-friendly tuning environments, operator faceplates, and loop diagnostics through RTune and CL diagnostics. PID tuning is visual and intuitive, and loop simulation helps validate changes. Its architecture emphasizes operator accessibility and tuning transparency. Invensys Foxborough offers tools like Loop View, Control Expert, and integration with Connoisseur for advanced process control diagnostics. These tools allow plant-wide loop assessment, model-based tuning, and constraint visualization. However, they may require more specialized knowledge to use effectively. For hybrid teams, operators and engineers, Honeywell offers more immediate usability. For centralized control teams or plants with high process engineering sophistication, Foxborough's toolset offers deeper diagnostics and advanced tuning capabilities. Real-world implications. In refineries, utilities, and continuous process plants, where override protection and constraint handling are critical, Invensys Foxborough systems provide exceptionally reliable and mature constraint logic frameworks. In batch operations, multi-product facilities, and fast tuning environments, Honeywell's streamlined PID integration, intuitive interfaces, and plug-in cascade structures support quicker commissioning and easier loop management. For legacy migrations, Foxborough's retention of the series algorithm may reduce retuning efforts. Honeywell, however, supports TDC migration paths with embedded tools for mapping old loop behavior into Experian logic. Where derivative action or setpoint ramping is common, e.g., furnace loops, polymer reactors, Honeywell's Type-C PID and filtering logic provides safer default behavior. Conclusion: Honeywell and Invensys present two distinct approaches to advanced control. Honeywell Experian focuses on simplicity, integration, and operator confidence. It is designed for fast deployment, consistent tuning, and ease of use in structured process environments. Invensys Foxborough emphasizes legacy continuity, control robustness, and deep override logic, making it ideal for demanding applications requiring high reliability and granular control engineering. Both systems are capable of world-class performance. The choice depends on the plant's operational philosophy. Honeywell offers modern elegance with embedded intelligence, while Invensys provides industrial depth and legacy power for environments demanding ultimate control over constraint and override behavior.